Hello, greetings. My name is Dr. Paschal Offor, and this is an A-level further math tutorial. We are still on equilibrium of a rigid body, and our topic is the center of mass of an arc. By an arc, I mean an arc of a circle. And our prerequisite knowledge is students in this class can calculate the center of mass of a sector-shaped laminar. This is we have treated. This is a topic we treated in our previous tutorial. Center of mass of a sector-shaped laminar. So it is my assumption is that my students, any student attending this class or seeing this tutorial should be able to calculate the center of mass of a sector-based laminar, or rather a sector-shaped laminar. And our specific objective is at the end of the lesson, students should be able to calculate the center of mass of an arc of a circle. Okay, now let's just go straight to what we've got. We have, let's consider a uniform wire. What I'm going to bring up here now. So I want to consider a uniform wire. Okay, so this is why I'm considering I have this. Okay, and this is a wire. You can see that I have just, first of all, I've made it straight. It's a very straight wire, and we say it's uniform in the sense that the mass is evenly spread along its length. We are not talking about the area or the volume here. It's not a solid. We mean just a thin wire. Okay, and this wire um, this wire can be used to form different shapes. It can be used to form a circle. See the circle here? The wire can be used to form a circle. And the wire when it is straight, and my assumption throughout this lesson is that every shape I'm using is uniform. Okay, so I'm talking about uniform wire now. Because it is uniform. The center of mass is in the middle of this wire as it is straight. It's exactly on this wire and is in the middle, the center of mass. But when it is used to form this circle, the circle I'm having here, this circle here, the center of mass will just come straight to the center of the circle it has formed. It will come straight to the center of the circle as I have just drawn here. You can see the axis, the y and x axis. You see where they have met. Okay, that is the center of the circle. Um, the the origin, we usually call it origin, the Cartesian plane. And you know that a circle has infinitely, many lines of symmetry. Okay, as far as you can draw a diameter, you've got a line of symmetry of a circle. Fine. And all these lines of symmetry meet at the center of the circle. That is to say that the diameters will always meet at the center of the circle. And that is where the center, the center of the circle is where the you have the center of mass. Okay. And don't forget that center of mass will always like if the shape has a line of symmetry, it will definitely be on the line of symmetry. Okay. Uh, yeah, it will definitely be on the line of symmetry. Now, if this wire, if it is not used to make a circle, if it is just used to um, make a shape like this, just like an arc like this arc here is the arc I'm talking about here. This is like a semicircle, okay? If it's used to make an arc like this, it will no longer be at the center. It will no longer be at the center. It will shift, and definitely it will not be on the wire itself, the arc. Okay, so this is the arc now. I'm just trying to place axis on the arc that I have drawn. So this is the arc here, and I'm placing axis on the arc. So this is the axis. I placed axis, the x and y axis. Okay, the y-axis on this arc now, because of the way the arc is facing, okay, the y-axis is the line of symmetry there, and therefore the center of mass will lie somewhere on this y-axis. Okay, is a line of symmetry that will lie somewhere on the y-axis. And it will be very easy to calculate the center of mass here, okay? Because it's lying on the axis. One of the coordinates will be 0. X coordinate, of course, will be 0. Okay, so it becomes easy. You only have to find y coordinate. And if it is shaped like this, this is still like a semicircle. Okay, I mean to draw a semicircle here. And the center of mass, as I said, also is no longer in the middle, like the circle. It has shifted, but it will definitely be on the line of symmetry. The line of symmetry of this particular semicircle that's facing this way is the x-axis. What I'm going to show us now is the x-axis. This is the line of symmetry. Okay, so yeah, the x-axis is the line of symmetry. So the center of mass will be somewhere on the x-axis, the line of symmetry. I like using this type to do my modeling. Okay, I like using this to do my modeling. It makes it. You can as well use the one I just showed on where the center of mass is on the y-axis to also do do your modeling. You can as well use that one. So it's as easy as using this one, using the one where x is the line of sorry, x-axis is the line of symmetry. Okay, any of them can be used, and both of them are equally easy. The one that may be a little difficult is where you find it difficult to place your axis. Okay, it becomes a little difficult. So I wouldn't like to use such. For example, let me give an example here. Let me push this away and give an example. If I have an arc, like this, the semicircle is faced this way. I wouldn't want to use this to do my modeling. I would like to use this one, or the one where y-axis is the line of symmetry to do my modeling and all that. When I'm done modeling it, then I can use it to use the result, any result I've got, to now find anyone at all can be found. As far as you have a standard result, you can use it to find anyone. So there's a point I just need to make here. If the flatter the curve, this it used to be a straight line. It's a straight line. It's a straight wire. It's a straight wire which can be used to. I'm trying to use it. In fact, the topic is arc of a circle. The topic is arc of a circle. So the straight wire can bending a straight wire now, uniform straight wire to form an arc. So I've got an arc here. This is exactly what I'm setting out to work on. Okay, I'm setting out to find a center of mass. It's something like this. Okay, any of this, even this is an arc. So it has a shape of a semicircle. Is an arc. I don't know, arcs. So now, the flatter it is, that is this one here, which is flatter than the semicircle here. So the flatter it is, the closer the center of mass is to the rod itself, or rather to the wire itself. Okay, and when it gets finally flat, as in it gets finally straight, the center of mass will lie exactly on the rod and definitely in the middle because it's uniform. If it curves, the more it curves, the more the center of mass shifts away from the wire and gets close to the center, the axis, the center of the axis. That's the origin. Okay, that is why if we got a circle, complete circle, the center of mass comes straight to comes exactly at the coordinate. So let me just concentrate this. Let me just focus on this. Focus on the arc. Let me just focus on the arc of a circle. Sorry, yes, of the arc, the flatter one, this one now. Okay, so we want to find the center of mass of this. And I'm going to make it look like this. I'm going to place my axis here. I'm going to place my axis. I'm going to place my axis. So I have just placed axis there. And okay. So I've just placed my axis here. So you can see that intentionally, I have just used an arc because I want to carry out a little modeling here. So, and I need an arc where I can place my axis, especially the x-axis, to be the line of symmetry. So my x-axis here is the line of symmetry. Okay, as you can see, it's just my line of symmetry, and the the center of mass will lie somewhere on the x-axis that I'm shading. It will lie somewhere there. Okay, center of mass will just be somewhere on this line of symmetry. Okay, so the center of mass, so let me just call it G, will just be somewhere here. Okay, and then I have my X bar, and I will have my Y bar. But incidentally, my Y bar will be 0 because it's on X axis. My Y bar will be 0. So calculations will be easy for me. I'll just definitely have to find the X bar. It's just X bar I want to find. So let's go straight to, let me get something that contain. Okay, let's just consider this now. I have another diagram to look at. So we have this that I snipped from my book. I have this is the arc now. Okay, and my target is to find the center of mass of this arc. So I will call the center of mass G. I will use capital X bar and capital Y bar. Capital Y bar. Where the capital word? So capital Y bar. But because it's going to be on the x-axis, my Y bar will be 0. My Y bar will be 0. So I will only try to find X bar then. I'll try to find X bar. Okay. So X bar is what I'm looking for. I'm setting out to find. Now, to get this, you can see the picture I have drawn here. I have just I've just mapped out a little portion of this sector, this arc now, a little portion, and the portion is here. I need to give color to this. Look at this portion here. See the portion here. It is so small that the angle theta is so small that that portion I have marked with red is almost like a straight line. It's not curved. It's so small that it is not curved. Okay. Now, it's instead of curved like this, is the angle, the theta. I want it to be so small, so minimized that the arc will just be almost like a straight line. The implication, therefore, is that the center of mass of that small arc will approximately be on the line. So this is the small line here. This is the small line. The center of mass will approximately be on the line. So it's approximately here. And I want to call it G X bar, Y bar. Okay. Now, my Y bar is this Y coordinate. Is Y coordinates here. Sorry. So we have Y coordinate here. This is where my Y bar is. My X bar is somewhere here. X bar. My X bar is somewhere here. Okay. And my Y bar is this. Now, of course, my Y bar here is not 0. My X bar is not 0. Okay. This small X bar and my Y bar, they're not 0. Now, I want to find the coordinate of this X bar, and I need to find X bar, what X bar is. This whole of this angle here is theta plus, remember, is in the middle. is in the middle of this line. So it will be the theta over 2 because it's in the middle. It's in the middle like this. So it's the theta over 2. The whole of this angle, the angle I'm looking for, the angle here is the theta over 2. And the length here is r, radius is r. And I'm considering an arc where here is alpha and up here is also alpha. Is also alpha. So I've got, therefore, OX, that is X bar here, the length here, the length of that X bar will be equal to, is equal to R cos theta plus the theta over 2. And this is approximate because I have so minimized the theta that it tends to 0. So the theta over 2 actually tends to 0. So it's approximately R cos theta. That is the length. And the mass of that small sector, remember, to find the mass of that small arc, rather, not the sector, the small arc. The small arc here subtends an angle of the theta. Therefore, the length of this arc is equal to the theta all over 2 pi, 360 degrees, which is 2 pi. I'm working with in radians, times 2 pi r. Okay, so this will give me r the theta. That's what it gives me, r the theta. That's the length. Therefore, the mass of that arc, the mass is equal to r the theta rho. That's the mass. So now it means I'm having okay, it means I'm having this for that rod, and I'm having mass this, and I'm having the center of mass as r, the x bar now, which is r cos theta. Then y bar, which I have not gotten. And indeed, I don't intend to get y bar. I will tell us why. I want to work with only x bar. I'll tell us why once I start taking the moment. Now, to take the moment of the mass or the weight of this arc, we have to take it above the y-axis. Will give us r the theta rho times, I'll use dot for times r cos theta. Now, it is with this arc, this small arc that we are talking about, that subtends an angle of the theta, can be drawn. In fact, there are infinitely many of them that make up this small arc here, the small arc here that we're talking about that subtends this angle, the theta. The theta is so small that there are infinitely many of these arcs. And to sum the moments, we need integration. So we have integral. And because this alpha here, this is minus alpha to alpha. Then r d theta rho times r cos theta. This is what is going to give me summing the moment. Now, the entire sector that we got, the entire sector has this area. Remember the formula to find, sorry, has the length, the entire, not the sector, rather, the entire arc. The entire arc, the whole arc has substance angle of 2 alpha. Substance angle of 2 alpha. So we've got 2 alpha. And the length, it has the length using the calculation 2 alpha over 2 pi. That is theta over 360. Like saying from elementary math, theta over 360. 2 alpha over 2 pi times 2 pi r. So it gives us, it has the entire sector, we have it has 2 alpha r, and therefore the mass 2 alpha r, therefore the mass is 2 alpha r rho. That is the mass. Okay. And if you take the moment about the y-axis, you will have this equation with the moments. You will have 2 alpha for all of them. For the entire sector, we have 2 alpha r rho times x bar. The x bar I'm talking about now is capital X bar that I want to find, I'm setting out to find, is equal to the sum of this, that's the integral, alpha minus alpha, r the theta rho, r cos theta. Okay, so I can cancel r and rho, these ones with this. I can cancel them. And I will have, then you will have alpha minus alpha r cos theta, the theta. And this gives us r sine theta. We evaluate from minus alpha to alpha. And this will give us, this means that 2 alpha x bar, capital X bar, is equal to r sine alpha minus sine minus alpha, sine minus alpha. And this gives us 2r sine alpha. 2 will cancel 2. So my x bar is equal to r sine alpha over alpha. This is the result. This is the center of mass of an arc. Remember, the arc subtends an angle of 2 alpha. And remember again that this x bar is on the x-axis. That means that y bar is equal to 0. The reason why we don't want to take the moment about the x-axis is because we already know. Remember, when we take moment about the y-axis, our target is to find x bar. And if we want to take moment about the x-axis, our target will be to find y bar. But we already know that y bar is on the x-axis. Sorry, y bar, we already know that the center of mass is on the x-axis, which is the line of symmetry. And anywhere on the x-axis, y bar is equal to 0. Y is equal to 0. That's the y coordinate is equal to 0. We already know very well that the center of mass is on the x-axis, which is a line of symmetry here. And for that reason, y bar is 0. So there is no need going to find y bar when we already know what it should be. Okay, now let's take an example. Let's see how this example goes. Got this example. The letter P is constructed using a uniform straight piece of wire of length 4A. The length of this wire is 4A. In that case, since here is 2A, therefore here must be 2a. It must be 2a as well. Then for a joint to another piece of uniform wire that is bent into a semicircle of radius, the radius is a. So here is the center, therefore here is a. Okay, and given that the semicircular piece of wire is 3 times as dense as, or they said there is 3 times as dense as, is 3 times as dense as the straight wire. Find the center of mass relative to the point O, relative to the origin. Okay, now I have, here is the origin here. Here is the origin. So this line here coincides with the y-axis. Here is my x-axis. That is my x-axis. Okay, the length there, the length of this wire is, the length of the straight wire, the length is 4. 4a rather, the length is 4. Therefore, the mass, if the unit mass is rho, the mass is 4a rho. Okay? And the center of mass will be in the middle because it's a straight wire and it's uniform. Be in the middle. This place I'm drawing now. Since the length is 4a, the center of mass should be where you have 2a. But since this is the y-axis, this is the y-axis, x coordinate is 0. So my center of mass G 0, 2a. That's the center of mass. That is for the straight wire. Now, for the semicircular wire, remember that the semicircular wire is 3 times as dense as the straight wire. So if the unit mass of the dense wire is rho, the unit mass of the semicircular wire is 3 rho. But first of all, we have to find the length. The length is a semicircle. Length of a circle is 2 pi r. So length of a semicircle is half of this, which is equal to pi r. Therefore, the mass is equal to pi r times 3 rho. 3 pi r rho. That's the mass. Now we need to find our center of mass. That is where we need to find our center of mass. Center of mass will be somewhere on this. This is the line of symmetry. Let me draw the P here. Let me draw the shape here. Something like this. So center of mass is somewhere along this line of symmetry, somewhere here. Okay, let's just put it somewhere here, G. Okay, so somewhere there, the y-axis, the y coordinate will be 3a. The x coordinate is what we need to find. Using the formula we got there, r x bar is equal to r sine alpha all over alpha. Remember that in this, the angle subtends is the angle that is subtended by the sector is 2 alpha. And in this case, we are having pi because it's a semicircle. So the angle in a semicircle is pi. Therefore, my alpha is pi over 2. Okay. Now, x bar here is equal to, my radius is a sine pi over 2 over pi over 2. Sine pi over 2 is sine 90 is 1. So you have a over pi. Okay, so that's the length of this arc, of this semicircular arc. Therefore, the mass, oh, sorry, it is not even the length. It is the center. We have gotten the length rather. Oh, I'm sorry. I'm talking about the center of mass now. So the x-axis, the x coordinate is 2a over pi. Okay. So this is the x coordinate. If you bring it down to, so I called here, oh, if you bring it down to axis, say it means that this is the x coordinate, x bar, and y coordinate, y bar. Y bar is 3a, and x coordinate is 2a over pi. Okay, so the g now, so for this semicircle here, the mass is 3 pi r, and the center of mass is 2a over pi, comma, and 3a. This is the center of mass. So now we're going to take moment for both x-axis and moment about the x-axis. We also take moment about the y-axis. Now, about the y-axis, moment. For the, first of all, before we do this, we need to know the total mass. Total mass. The total mass is equal to mass of the line of the straight wire, which is 4a rho plus okay, the r radius is a. So I'm meant to put, let's just change this r to a. So let's put it a. Okay. So now the total mass is 4 plus 3 pi a rho. That's the total mass. 4 plus 3 pi a rho. And we want to find the center of mass of the entire shape. So we are looking for x bar, y bar. Those are what I'm looking for. So taking moment about the y-axis, for the straight line, the mass is 4a rho, and the x coordinate is 0, so it's times 0, plus for the curve, the mass is 3 pi a rho, and we have the x coordinate is a over pi, and this is equal to um, 4 plus 3 pi a rho x bar. I want to use capital X, x bar, okay? And this x bar we want to find, cancel the arrows. In fact, there's nothing to cancel here. We have 0 here, okay? I can cancel pi here too. So I'm having x bar to be equal to 6a over 4 plus 3 pi. This is my x bar. So let me write it out somewhere here. Let me record it somewhere here. X bar is 6a over 4 plus 3 pi. Okay, so we'll also take moment about the x-axis. Take moment about the x-axis. Now, about the x-axis, we have x-axis. We have the first one again, the straight wire 4a rho times 2a. Now plus the curve 3 pi a rho times 3a. And this will give us the total 4 plus 3 pi a rho y bar. I can cancel arrows. All the arrows, I can cancel them. And I'll be having 8a plus 9 pi. Is it 9 pi a? Is 9 pi a is equal to 4 plus 3 pi y rho. Therefore, my y rho is equal to 8 plus 9 pi a all over 4 plus 3 pi. Okay, so we've gotten our x bar and we've gotten our y bar. So those are the coordinates of the center of mass. We'll stop this tutorial here. Catch you next class. Thank you.